Today's problem, majority element more than n over 3. Difficulty medium. Given an array consisting of n integers, the task is to find all the array elements which occur more than floor of n over 3 times. Okay? Returned array should be sorted. Examples. So this one right here. 1, 2, 3, 4. There are 8 elements. 8 divided by 3. Floor it is 2. So how many has to be more than n over 3? So there's 3 2's. There's 3 1's. So that's the answer to that one. This one, -5. This one, well, this answers a good question, which is what if there's no majority element? And we get actually an empty array list, because actually the Java code, the method signature, wants an array list as the return type. Array size between 1 and 1,000,000. Array, let's see, the array elements can be between -10 to the 5th and 10 to the 5th. Expected complexities should be linear. Auxiliary space, O of 1. That's interesting. All right. Topic tags. So what surprises me here is the topic tag hash, because I think you could do it with a hash map, and it might very well work. Just go through the array, put the numbers in a hash map, keep track of the counts, and then go through the hash map and see which numbers have a count greater than n over 3. But that is definitely not O of 1 with regard to auxiliary space. It's going to be, O of n. So we're going to do it. We're not going to do it with a hash map anyway. Majority element. So the majority element question is pretty common. Usually it's just here's an array. Find the element, if there is one, that occurs more than it would be more than n over 2, that occurs more than what am I trying to say? It occurs in at least half. I'm sorry, more than half of the array elements. This one is more than n over 3. So let's first observe that the most the most you can get here would be 2 elements, because you can't have 3 elements that occur more than n over 3 times. We're going to use something called Boyer-Moore voting algorithm. You can do the majority element problem with Boyer-Moore also, although there are other ways to do it. It's not the most common way of doing it, but for this one, well, if somebody said like O of 1 on the space, then yeah, I don't know. Anyway, we're going to use an extended Boyer-Moore voting algorithm. We'll go through how it works with example 1 here. Now, O of 1, as we've covered before, doesn't necessarily mean that you only get one extra variable to as far as auxiliary space. It just means that the auxiliary space doesn't vary. It doesn't get bigger as the input gets bigger. So we're using a few variables here, but they're unrelated to the input size. So let's pull this. Is this whole thing visible here? That one's kind of long. I need to get the array has to be visible, and all the code has to be visible. All right. So let's go through this. Let me get a pen. Okay, there we go. Let's see. So we're going to iterate through the array for the first number, 2. Does that equal candidate 1? No. Does it equal candidate 2? No. Those are both 0. Does count 1 equal 0? Yes. So candidate 1 is going to become 2, and count 1 is going to be 1. Right? That is the whole loop, isn't it? Not missing anything down here. No, we got to go through this for loop. Okay, whoops, let me line that up again. Okay. Next number, let's see, we did 2. The next number is also 2. Does num equal candidate 1? Yes. In that case, increment count 1. Next number, 3. Does that equal candidate 1? No. Does it equal candidate 2? No. Count 1 is 0? No. Count 2 is 0? Yes. So now candidate 2 becomes the number 3. And count 2 becomes 1. 1. All right, next number, 1. Let's see. Does that equal candidate 1? No. Candidate 2? No. Count 1 is 0? No. Count 2 is 0? No. Okay, in that case, we're going to decrement count 1 and count 2. What that means is that there's a new up-and-coming candidate, and so maybe these candidates that we got first, just because they occurred first, maybe they're not as great as we thought. So we're going to decrement. All right? Next number, 3. 3 equals candidate 2. So count 2 is going to go back up to 1. All right, next number, 2. 2 equals candidate 1, so count 1 goes up again, and count 1 is 2. Next number is 1. None of these are true, and what is going to happen now is we are going to decrement count 1 and count 2. So count 1 will become 1, and count 2, I'm just going to round it out here, 0. Okay, last number, 1. Now that doesn't equal candidate 1 or candidate 2. Is count 1 equals 0? No. Is count 2 equals 0? Yes. So candidate 2 now becomes not 3, but 1. Count 2 becomes 1. And we are done. So keep in mind our candidates here, because I'm going to have to scroll it, but our candidates are candidate 1 is 2 and candidate 2 is 1. All right. Those are unfortunately not going to like scroll off the page, although the page will scroll. So I'm going to have to remove those. Candidate 1 is 2. Candidate 2 is 1. All right, let's go back to this. And let's see what we have. All right, so yeah, we're going to start over. Reinitialize count 1 and count 2. All right? We're going to take one more pass through the array, and every time we see candidate 1, we're going to increment count 1. Every time we see candidate 2, we're going to increment count 2. Now, rather than do that one at a time, the counts that we're going to get would be for candidate 1 is 3, and count 2 here is also going to be 3. Let's see, is count 1 greater than array length divided by 3? Yes. So we will add candidate 1, which is 2, to the result. All right, here's our result over here. I'm keeping track of it. So far there's a 2 in it. The reason we have to do it this way really is, well, no, that's not the only way. That's not the only reason. Okay, if candidate 1 is not equal to candidate 2, it's possible with the algorithm that candidate 1 and 2 wind up being the same, but in our case, candidate 1 is not equal to candidate 2, and count 2 is also greater than array length divided by 3. Because we're asked to present the result in sorted order, then if candidate 1, which is 2, is less than candidate 2, which is 1, that is not the case. So we go into the else and we add at index 0, we put it ahead of candidate 2. So that would be our answer, 1 and 2. And actually, can I scroll this? I can't. I can't. Actually, I mean, I can scroll it, but let me just pull this over here. All right, so there it is. Yeah, answer 1 and 2. Okay, let's get rid of the annotations and run it. Okay, majority element, extended Boyer Moore algorithm, O of 1 for auxiliary space. That's it. Please like the video, subscribe. I'll send you problems of the day every weekday, and we'll see you next time.